Can you hear me? Cool. So my name is Matan. I am leading the Crimson project, and today I will be giving up a brief overview and a status update about what's going on recently with the project. So let's start with the usual background we do with the Crimson project. So these are some famous slides we have. We start with the storage speed trends. We all are aware that storage is shifting, is changing rapidly. So we started with hard disk, which can draw around like 150 to 100 IOPS, IO operation per second. Today we have NVMEs, which can draw a larger amount than that, larger throughput. Today, commercial NVMEs, we can reach almost 2 million IOPS per second. So it's a completely different storage device in mind. I will note that when Ceph was originally architected, it was targeting hard disks. So from a different perspective, we have CPUs. So for a CPU with a clock speed of 3 gigahertz, meaning 3 billion cycles per second, the budget, meaning how many cycles we can allow ourselves to spend for a single I/O. So for hard disks, we can allow ourselves to spend lots of cycles. This is around 15 millions. But for NVMEs, the story is different, and we can allow to spend only 2,000, meaning we need to be much more efficient and quicker in terms of CPU efficiency. Another famous slide here. This is for anyone who's been following CPU trends. This is the 50 years of microprocessor trend data. So some trends here. We have the orange one, which is the transistor count. This is also called Moore's law, which says that the number of transistors will double itself every around 2 years, and this is in fact the case. But for us, the interesting things are the black trend and the blue trend. So the black trend represents the number of logical cores. So we can see CPUs today doubling in the number of cores they are having, but the blue trend represents the throughput per core. We can see that the throughput per core actually started to plateau around 2008. So we have more total throughput, but what we care here is the raw throughput we have per core. Ceph today can drive large amount of throughput, but it also needs large amount of resources, and our goal is to make better usage of these resources, of this large number of cores. So essentially, Crimson is how we are planning to do this. Our goal is to minimize the CPU overhead per single I/O by avoiding context switches, and for us to exploit faster and newer storage devices. And how we are doing this? So Crimson is a drop-in replacement to the classical Ceph OSD we have today. Essentially, it's a rewrite from scratch we have for the OSD component, which is responsible for the I/O path. This is, as I said, efficient rewrite using the C* framework. C* framework is a C++ asynchronous framework, which will help us with this goal. And it will keep in mind we have the single thread per core architecture, which will allow us to avoid this heavy overhead we have with the threading model we have today, which I will explain now. So in order for us to understand better where the overheads come in play, so I will talk a bit about the OSD architecture. I won't go too deep into this subject, but for us to understand the I/O path, we need to understand these three main components. So we have the messenger, which sends message between daemons, send message between clients, between OSD, monitor, and so forth. It's the communication layer. We have the PGs, which implement the consistency protocols, which is basically where all the magic happens in terms of I/O replication, failure recovery, request ordering, so forth. And lastly, the object store. The object store is a transactional interface. This is where the actual I/O gets submitted to the storage device. We have now today Blue Store, which Nia also talked about. Previously, we had File Store, and I will talk in the last slide about C Store. So how the threading model comes in play. So considering a write, which is coming to Ceph OSD from a client, the messenger will pick up the message from the wire using a messenger thread. Later on, it will put this message on a queue, on a thread pool queue, for a PG thread to collect it, to handle it, and to create a transaction. The transaction will be submitted to the object store. the object store will commit it, which is blue store, will commit it, and after the transaction has been committed, using a final thread, we send a reply back to the messenger queue to pick it up. Essentially, what we want to understand here, that we have a lot of thread pools, and each thread transfer requires inter-thread coordination over the context of the queue. And let's say with PG in particular, more than one thread may want to need to access the contents of the queue to understand what's going on. So I like this picture to explain what's going on. With the previous slide, it's much easier. We have theory in practice. In theory, the programming model is not acting as much as we would expect. Unscalable programming practices, such as taking logs, may prevent our application from scaling up to many cores. And we have a lot of races in terms of the resources we have now. And to explain how Crimson does it, so in the left side, we see we have in the second stage, this is from a different slide, from a different slideshow, so we have a request being done to the disk. Now, while we wait for the I/O to complete in the disk, we have a context switch in our core. This may draw a lot of overhead. We need to copy, most significantly, the size of the block thread stack. And later on, once we're ready, we respond and we context switch back to this thread. Now, with Crimson, same story. We need to wait for the response from the storage device. However, here, we immediately return a future, which is an asynchronous concept that will allow us to do other work on the same core. This will be scheduled using the C-star framework, which is a user space scheduler, not like the classical OSD, which is an operation system scheduler, which is much heavier in terms of overhead and much more significant overhead than Crimson's one. So we can see this is how Crimson I/O path looks like. Each thread, each core can handle its own I/O path, all the phases in the I/O path separately, meaning there are no context switches, there are no locks, and when process pauses or logically blocked, meaning it waits for a response, it voluntarily yields for other tasks to do some other stuff, meaning it's a cooperative scheduler. So let's see how the CPU reacts to that. This is a slide, first slide from an RBD workload with 4K block size for random reads. That we see that for classical, this is the upper ones, we have 35,000 context switches per second in this workload. While with Crimson, we basically have none, apart from some from the operation system. Same with CPU migrations. We have 70,000 per second. A CPU migration is when a thread wakes up and it's being run on a different core than the one that it was ran beforehand. So with Crimson, because we run with one thread per core, we can see that we have also none of that. Same story with page faults. So we can see that the CPU can really utilize better these results, this behavior we have, the new architecture. So in terms of status, what do we have today in the project? So for Squid, the latest release, we will be tech reviewing Crimson for people to try it out. We support RBD workloads on replicated pools. We should support it fully. We also have multi-core support. Previous releases were able to run on a single core for easier to development reason. Now we have multi-core support, which allows us to scale. In terms of backends, we have BlueStore as a default, which is also the backend for classical. We have adapted it to use with Crimson. We have C-Store, which is in development. It's native to Crimson. It's rewritten using the C-Star framework. I'll explain about it soon. And we have CNStore, which is an in-memory backend, and not a real backend, only for development purposes, not really sending any IOs to disk. We also have quick deployments. By quick, I mean easy and nice and friendly. Because Crimson needs to know which CPUs are available, we expected users to really mask which CPUs should be used. It's not so much friendly, and once you have many OSDs, so it becomes quite a problem. So this is the term quick now. It's being done in a more automatic fashion, and now we can just strictly deploy Crimson OSD and let the scheduler find the available cores and do that work for you. So we can deploy it via Ceph ADM, Rook, and vStart also for development purposes. Initial scrub support, which is also cool. We have more stuff to work on, like repairing and automatic scheduling, but it really helps us to scrub in the end of test to find any missing pieces. Also, recovery and backfill is there, it's supported, and there's a lot of work that was done recently to support all the edge cases, which are now stable. So in terms of test coverage, we have a stable suite we tend to maintain, which we have all the basic tests there, the trash test of OSD, the recovery patterns, as I said. The test help us to avoid any regression. That's why we use PR gating since the RIF release to not merge anything based on its appearance, but we actually have a stable suite, which was a major goal back in RIF. And we added recovery trashing patterns now that it's already stable. Last thing, CStore also now run as part of the QA suite. So that means we run with BlueStore and with CStore. Each test is being run with 2 backends. Coroutines. So this slide was intended to get you afraid a bit of the Crimson code because it's tricky. Using the C-style framework is hard. It's a new type of C++. If C++ is not friendly, so C-star is not friendly here. We have a lot of callbacks, we have a lot of captures, and it's really hard to read, write, and to debug. But with coroutines, with C++20, which introduced coroutines that allows for synchronous code to be executed asynchronously, the same code today looks like this. This is the same piece of code, so it's much easier to read and understand. I mean, at least for me for now, but it's easier than this slide for sure. So it really helps with development and should take the development of the program, of the project, to be quicker and have new developers join it. So the next step, we plan to expand the test coverage. We have the basic test there, but we need to keep expanding it, same as we have in Classic, where we are, our releases are stable thanks to the suite, so we want to gather as well. We have erasure coding pools, which is work being done, and it's almost there by Radek. And we have PG splitting and merging, also work being done by Ashwarya from the team. For now, the PG number is static. It allows us, again, to test, but it's not really scales over the size of the pool, so that's why it's work in progress. Lastly, performance. Multi-scale is there, stability is there. Our next goal is to really find the bottlenecks, which will allow us to really take the raw results, not the CPU profiling, but actual I/O result, into a different scale. So for experimental usage, this is a tech review, right? The project is not fully ready, so we have some required flags that will prevent anyone to mistakenly use it in production real data. There is this really long flag to enable unrecoverable features, so forth. It's in the documentation that we don't want people to actually deploy Crimson OSD, start it, get some issues, and then we won't be able to support it because it's still under development. So you need to be really aware that you are deploying a tech preview version of the OSD, and otherwise the OSD won't come up, the PGs won't come up, and you won't be able to do nothing. And in terms of upstream release support, so we are merging everything to main, and we tend to backport everything to the Squid release. So it's the same release, but with a bit of a delay. So the second part of the project, we'll talk about the one layer below. This is the object store. So today we have BlueStore with Classic. As I said, this is the default object store. BlueStore is good, it's stable, and it's working well in the end. But the problem for us is that it's suited for the classical OSD architecture. Because of its threading model, which I showed earlier, it's not really native to the Crimson OSD. It has a CPU-heavy compaction behavior, and the RocksDB in general is heavy in terms of CPU usage, dependence in BlueStore. And lastly, I will note that BlueStore is still being improved. As Nia showed in her slide, there's a lot of work being done there to make it work better. But for us in Crimson, overcoming the RocksDB dependency would be a huge step. So Crimson with BlueStore. Crimson is compatible with BlueStore. It allows us to have comparison, a real comparison with Classic running the same backend underneath. It's using a kind of a hack. It's backed by a thread pool, but the thread pool is not managed by the C-star framework. So it's really not optimal. We just kind of did it for us to have a backend. For now, this is the intermediate backend point. We will probably be able, and we are able, to have the same output as classical OSD has with BlueStore. But for us, really, it's the throughput bottleneck. Unless we will really submit IOs using a futurized C-star framework using backend, we won't be able to show the real potential of this upper layer of the OSD. So that's why we come up with C-Store. C-Store is a new reroute to the backend now. So this is really the second half of the Crimson project. This is a Crimson architecture native, meaning it's rewritten using the C-Star framework. It should scale better than BlueStore with RocksDB because it has none of this. It should support emerging storage technologies like NVMe and so forth. And the metadata structure will be stored as B-trees, which should be much more efficient. This is the comparison of the design, simplified one, of course. I won't go deeper into the architecture. If anyone is curious, it's all in the documentation. We have code walkthroughs and so forth, but just to get the better sense of it, with BlueStore, we store the metadata with RocksDB key value pairs, and the RocksDB database reside on small BlueFS partition in the small device, in the storage device. With C-Store, both data and metadata are going straight into the transaction manager, which is managed by the C-Star framework. So the current status of C-Store. So C-Store is currently development led by Yingxin from Intel. Intel is also helping us to develop this project and is doing a great job there. So stability is today C-Store support all the basic API tests, all the features we have in the backend such as snapshots, and it's part of the testing suite as I mentioned earlier. Tiering support is there. A major goal is to support heterogeneous configuration, like putting a small amount of more stronger kind of storage devices and a larger amount of the lower endurance storage devices. And we have multi-core support, same as we have in the Crimson OSD. So it kind of aligns in the same pattern. The next steps. So stability and CI, again, if we don't have any stabilized CI test suite, it doesn't really mean anything. So continue to expand the test to find all the missing pieces. Performance and profiling. Now that we start to become more stable in terms of C-Store development, we want to really understand where our numbers at, where we stand, where the bottlenecks are at, write amplification, all this kind of good stuff that we need to work on to really get the results there. Dynamic sharding, meaning we can switch, same as we have in the Crimson OSD. Now the number of the shards, number of the cores we have that C-Store is deployed on is static. We need to work on making it more dynamic and more efficient device tiering. There are some approaches to how to make the tiering really better usage with C-Store. So I will finish here. This is kind of big picture roadmap we have. So for Reef, we started with to support a basic workload, which is RBD with replication. We added the test suite. We added some snapshot support. For Squid, we're officially having some kind of officially tech review, which is good news, yay. Stability, so continuing with stability, we have recovery and backfill support and scrub support. And later on with T and more, we have full scrub support, EC support, PG, and again, performance. That's why we are here. We want to really show the benefit of using Crimson with faster and larger storage devices. So if you're not afraid of the slide and you want to join us, we have the tracker where all the work in progress is there, all the bugs, all what we currently know is not stable, and we are working it in the tracker. Documentation if you want to read any further, and we have the Slack and the weekly meetings. We meet there. That's it. Thank you.
Awesome. Thank you, Matan. Anybody got any questions?
So, as far as I understand, we're working heavily on C-Store. So where we are at the performance level compared to Classic right now?
So now we currently run with default with BlueStore because it's stable and it allows us to focus on the OSD actual development. The numbers there are the same, and we even surpassed by a bit the classical OSD. But again, this is not the final goal we want to intend. So now we should have the same results, even better, thanks to some caching behaviors and so forth. But the interesting kind of numbers will be C-Store ones. And for this, this is the time we start to evaluate and to understand better where we stand with C-store now that it's stable in a way.